Yeah, so thank you very much. It's a great honor and pleasure to be here today and give a talk. And I want to speak, as you said, about geometric representation of structured extensions. And I want to start, by saying the people who I work with. So this is Nikolai Edeko from the University of Zurich and Asgar Jamneshan from Koç University in Istanbul. And now I want to start by explaining what I really mean by structuredness here in this talk or in the context of measure-preserving systems. And this is the first part of my talk. So this is structured ergodic systems. And in this context, there's the following theorem, which is probably known to many of you due to Paul Halmosch and John von Neumann. So theorem, so-called Halmosch-von Neumann representation theorem, which was actually proven while both of them were here at this institute. So Halmosch and von Neumann from the year 1942. And they considered an ergodic transformation, an automorphism of a probability space. So let phi from x to x be an ergodic automorphism of some probability space x. And they looked at the induced operator on the L2 space, T phi from L2 of x to L2 of x, which just takes a function and pulls it back with phi, the so-called Koopman operator, which had been introduced 10 years earlier by Bernhard Koopman. Koopman operator. Now they looked at systems for which this operator has a very nice, simple and structured behavior, the so-called systems with pure point spectrum or discrete spectrum, or you might also know them as compact systems or isometric systems. It's all the same. So, but let me write again what this means. So the operator or the system has a discrete spectrum. If I now take all the eigenspaces of my operator, so of course on the eigenspaces the operator acts in the most simple way I can imagine, just by multiplication with a number. Now the point is that my whole space is already generated by these. So if I take the closed linear hull of these eigenspaces, then I already obtain my whole space L2 of x. And now they observed that this is precisely the case if the system is isomorphic to a rotational system. So this is the theorem. So yeah, this is equivalent to the system x phi being isomorphic to a rotational system on a compact group. So I will write this down as follows. So I have the compact group H, I have the Haar measure, and I have the dynamic given by rotation. So I will, so H is the compact group with Haar measure lambda H, and C is just some element in the group, and my action is given by rotating from the left with this C. So for example, you take a unit circle and you rotate every element around the same angle. Okay, so this was a very important theorem in the history of ergodic theory, inspired many new results, and it also has generalizations to group actions, which I will come to in a moment. But let me highlight one subtlety here, and this is this isomorphism sign here. Because in the situation they were originally working in, they assumed certain separability restrictions on these spaces. So they looked at certain separability restrictions on their probability spaces. And then you can really understand this isomorphism as you have a map from X to H and a map from H to X, which are mutually inverse up to null sets. However, if you start from an arbitrary probability space, you have to be a bit careful and use a different notion of morphisms and isomorphisms of measure-preserving systems to make this statement correct. And I want to explain this by using now the following general definition of a measure-preserving system, which is an operator theoretic one, and basically inspired by the book of Tanja Eisner, Arlen Farkas, Markus Hase and Rainer Nagel from 2015 on operator theoretic aspects of ergodic theory. And what is the definition? So we take now an arbitrary group, and we say that a pair XT is now a measure preserving system if still X is a probability space, so X is probability space, but now G no longer acts directly on X, but rather by operators on the space L2 of X. So there's a difference now. Didn't go as planned. Okay, so T is now a representation of the group on the L2 space of X as operators, and these operators satisfy certain properties. So this representation is so-called Markov embeddings. Markov embeddings. And what do I mean by this? Well, these operators satisfy three properties. The first one being that they are isometries. So Tt of f has the same norm as f. Then Tt respects the absolute value or the modulus of a function. And finally, it also maps the unit, so the constant one function, to itself. So this is what I mean by a dynamical system in the following. And now 3 remarks. The first one, if you have a standard Borel space, standard Borel probability space, then every such operator, every such Markov embedding is actually the Koopman operator of the transformation of the space X. So really in this sense, this is a generalization of the standard framework. The second remark is that there are different equivalent approaches, for example, by Terry Tao and Shalom and Asgar Jamneshan, where they look at transformations of the measure algebra instead. So this is an equivalent approach. And there is another equivalent approach, but here I will choose this operator theoretic framework. First of all, because I like linear operators and I'm a functional analyst, but also because the notion of discrete spectrum is by definition a very functional analytic one. So it makes sense to use this approach here. And the third remark is, well, you might wonder why one should even do this generalization. So if you do applications, you are usually only looking at standard Borel probability spaces. So why do this? And one reason is that certain constructions, so for example, you saw in the talk by All last week, you can take certain ultra powers, or you could take some inductive limits, and then you end up with measure spaces which no longer have these properties, these separability properties. Or you could just say you take some measure on a Stone-Čech compactification, and then you also end up with something which is not separable. So these are reasons why you should look at the generalized version of a measure preserving system here. And we will do this in the following. So this was also one of the main goals of our project, to avoid such separability restrictions, because often you can work around the problem in applications, but it is, from my point of view, more satisfying if your structure theory applies to every measure preserving system on every probability space and every group, instead of just using a countable structure. Okay, so now I also want to say what an extension or a morphism between such systems is. So this is just the same. So if we have now two systems, let's call it YS and XT, then an extension between those is now also just Markov embedding J from L2 of Y into L2 of X. Markov embedding intertwining S at T. Intertwining the dynamics S and T. Okay, and now with this notion of extensions and then also isomorphisms, of course, this becomes, yes?
So you define this Markov embedding. If you know in addition that X is sufficiently separable,
Yes.
Can you make it a real?
Yes. So if you have a standard Borel probability space, then then really TT is just given by TT of F is just given by composition with some map phi t on the space X, which really is the measure preserving map and so on. So if you have the separable structure, you really do not get anything new, so to say.
Sorry, but except for this question.
Yes.
Suppose you're interested in T,
yes,
on who knows which space, but you are interested only in a certain function and whatever powers of T generate on that function.
Yes.
That's because that's insane.
Yeah. So this is
that's what you really.
Yeah, this is.
Then you fall down here.
Yes, exactly. So if you start from, let's say, a separable or a finally generated group, and you are just interested in averages, for example, then you can just take the orbits and the algebra or the space generated by that, and then you end up with the separable case again. Yes. So really, this is more for if you have either some inseparability in the group, or you take some constructions, for example, which lead out of this these standard Borel probability spaces.
Sorry, I'll ask you questions.
Yes.
This definition of this, so the norm you've written there is L2 norm?
Yes, exactly, precisely.
And is this equivalent, I presume there are many ways to say, is this equivalent to saying that it's automorphism of von Neumann algebra?
Yes, that's also the same. So you can also say you take, so this would be the third approach I didn't mention. So you could also take automorphisms of L infinity of the von Neumann algebra and instead of this, demand that the operators are multiplicative, so they respect the algebra structure. And here you have to assume that, of course, it also leaves the measure invariant. So this is basically, this encodes that it leaves the measure invariant.
Was your, on the left-hand board, was your group meant to be a billion? Or
no. So here this is just for C actions. So it's just one single transformation. I will come to the general version in a second. So yeah. So this was just for a single transformation, not for a group action here. But I will give you the full version now. So. Okay, so let me write this down. So this is the general version due to Mackey in the separable case, and then there's a functional analytic inseparable version by Nagel and Wolf from 1972, and yeah, basically the same thing as before. But so now let's say we have such a measure preserving system as I just defined, and say that it is ergodic. And ergodic now means that the invariant functions under my representation are just the constant functions, so there are no non-trivial invariant functions. So this is all F L2, which are left invariant by all operators. These are just constant functions. And then also I get the same equivalence. So my representation or my system has discrete spectrum. Discrete spectrum. And now I have to slightly change the definition. I will say this in a moment, but I then get the same equivalence. So this is equivalent to the system now being isomorphic again to a rotational system, but now here the non-abelian case comes into play. You might have to model out a closed subgroup. So you have a homogeneous space of a compact group. You have still the Hahn measure there and a rotational system. So here, I really mean here on the right-hand side, you really have a point-wise dynamics. So you really have dynamics on this group, and this induces you an operator theoretic system, and as such, it is isomorphic to the left-hand side. So this is how you should read this. So with, I will specify the data again. So H, a compact group, U, a closed subgroup of H Lambda here is the Haar measure on a homogeneous space, and C is now given again by rotation, but now of course your rotation depends on your time or your acting group. So C is now not just an element of the group, but rather a group homomorphism from G to H. So group homomorphism, which then induces your rotation. So at time T or at an element T of the group G, this action is given by just multiplying from the left with your group homomorphism. Okay, so and here discrete spectrum, you also have to slightly change. So instead of looking at the eigenspaces, which are no longer available here in this general framework, you have to look at finite dimensional invariant subspaces. So small, your dynamic is already determined by the small subspaces of your L2 spaces, of your L2 space. So if I take all the finite dimensional invariant subspace, so M is T invariant and finite dimensional, then these already generate the whole space L2 of X. Okay, so now, this is the general version of the Heimlich-von-Neumann theorem for general group actions. And now I want to give you a proof which is close to what Nagel and Wolf did, because we will use the same methods in the following results as well. So this, let me now give you a proof, or at least a sketch of the proof. And first, I should say that, of course, from B to A, this is just an application of the Peter-Weil theorem, which tells you that that the L2 space of a compact group, if you look at the left regular representation, this always decomposes into finite dimensional parts. So the first implication from B to A is really just an immediate consequence of the Peter-Weil theorem. So really the interesting direction is to come from A to B. And the path I take here is to use a topological approach. So the idea is to transition first to topological dynamics, then apply topological representation, and then change back to ergodic theory. So the first step is to transition to topological dynamics by using a topological model. And there is a standard way in this functional analytic framework to define such a model. You just have to find a suitable subalgebra of L infinity. So in this case, there's one which is obvious. We just take the finite dimensional invariant subspaces, but now those which are contained in L infinity of X, which are actually all because of the ergodicity. You can show that, but it doesn't really matter. In the end, you take these which are contained in L infinity, so M is T invariant and finite dimensional subspace, and this gives you a unital C-star subalgebra of L infinity, which is T invariant, and basically this standard procedure to build a topological model out of such C-star subalgebras, which is based on the Gelfand representation theorem. So then you can show by standard, I will just write down Gelfand. You can show that there is a topological model. So we have a compact space, and now an action of the group on K as continuous maps. So phi from G to the homeomorphisms of K, mapping an element to some map phi T. So, and an invariant measure on that space. Let's call it UK, invariant measure on K, such that the induced measure preserving system is isomorphic to our original system. So I find an isomorphism, let's call it phi, from my mu system, my topological model, K phi mu. And again, I should talk about the induced operator theoretic system here, but I will just write it down like this. And this is isomorphic to my original system. And this isomorphism has the property that it maps the continuous functions precisely to the algebra I started with. So the topological models are in one-to-one correspondence to unital C subalgebras, which are invariant, and I should also add dense in L2, and this is of course just satisfied because I started with a system with discrete spectrum. So in this way, there's a canonical way to change from ergodic theory to topological dynamics here, and to turn the properties into topological ones. So we may, in the end, assume without loss of generality by passing to the topological model that my system xt is actually induced by a topological system, just a topological system equipped with a suitable measure. And this topological system has now two properties. So the first one is that so the induced Koopman representation on the continuous functions now has discrete spectrum. So this now has discrete spectrum. This is by choice of my algebra B. And the second is that my system is now ergodic in a topological sense, because my original system had no invariant functions. Then in particular, my topological system does not have continuous invariant functions. So the invariant functions of my representation on the base of continuous functions is also just the constants now. So basically, I started from a measure preserving system which has discrete spectrum and is ergodic, and I ended up with a topological dynamical system which has discrete spectrum in a topological sense and is ergodic in a topological sense.
Yes, the upper part you deal with general group.
Yes.
The lower part you write T. So, and you say without.
Yeah. So T always refers to the representation of the group.
And then my question is I think in Mackey theorem, he assumes a locally compact case, and in Nagelwolf, what is assumed about the acting group?
I think it's put slightly different there. So you are right that actually the theorem due to Mackey is in that sense more general, that you can assume a locally compact group. So here in my talk, everything is discrete for reasons I can come.
It's actually not about what you still will tell us. I want to better understand. You said Nagelwolf is generalization. So what do they assume about the group?
I think so basically they already start from a subgroup of the bounded linear operators. So they say so this is in this more theorem about operator groups on Banach lattices.
So this maybe applies to so-called Polish groups?
Well, if the space is separable, then of course you can say that the strong operator topology is metrizable and on bounded sets, and then you end up with the Polish group in this way. But I'm not sure. So in the general case, this is not a Polish group what they look at, but I think, yeah, I'm not sure if it's not a real generalization if you look at locally compact groups. I'm not sure if this is covered in a more general version. So it's just a generalization of the case where the group is discrete. But yeah, I'm not sure. I would have to look up in the paper. So okay, so proceeding with the topological case here. So this was the first step to transition from ergodic theory to topological dynamics, and second step is now to use a topological representation theorem, or to prove. So a topological representation theorem. I'm having trouble with my words today. So assume now that we have such a system satisfying these two now topological assumptions of discrete spectrum and topological ergodicity. Then I want to show that the system is, as a topological dynamical system, isomorphic to a rotational system on a homogeneous space. And in topological dynamics, there's an easy and canonical way to construct a compact group in this situation, and this is due to Robert Ellis. So maybe you have heard about enveloping semigroups in some sense, but this is a canonical way to construct now your homogeneous space in a very easy way. So we look at the transformations we have. So these are all, of course, continuous maps from our space to itself. And the idea is now just to take the closure with respect to a suitable topology. So you could take the pointwise topology. This would be the classical semigroup due to Ellis. But here I will take the topology of uniform convergence or the compact open topology on that space and take the closure with respect to that. And in this way, I, in general, will only end up with some semigroup, which is not compact, but due to my assumptions, namely part one, the discrete spectrum part, tells me that this is actually a compact group in this situation. This is a compact group in this situation, and this is just a consequence of the Arzelà-Ascoli theorem, basically. Because if you have discrete spectrum, then your space is generated by finite dimensional subspaces, and in finite dimensional subspaces, bounded sets are relatively compact, and this translates to your operator representation having relatively compact orbits, and this translates to your dynamic being equicontinuous, and then in the end, this also means that this set is compact. So it's just the Arzelà-Ascoli theorem, basically, which you use here. And the second part of your assertions, the ergodicity assumption in the topological sense, shows that the canonical action of the group on your space K, which just takes a map and a point and evaluates the map at the point, this is transitive. So this is quite easy consequence of this irreducibility conditions which you have.
And so again, what do you assume here about the group G?
It's just a discrete group. So any discrete group.
Not necessarily count.
No. Okay. And if you have now these two things, then you have already found your group. And of course, H is also a compactification of G's in the sense that you have a group homomorphism from G to H, which just maps a T to phi T. So you also have your group homomorphism. It's just
so if my G is discrete R, then I end up with Born compactification.
I mean, it depends on which space you act on. So of course your space could be just one point, then it cannot be the Born compactification. So this is not necessarily ejected, this map.
But the most general thing will be
the most general thing would be the Born compactification. That's correct, yes. So
in that case, I'm still confused. If G is the integers,
yes,
can H be non-abelian?
And no, you're correct. So if you start within a abelian group, then also this will be abelian.
Yeah, that was why I was confused in the previous version of the theorem when you said that down here when you said that H can be non-abelian, but there's just a copy of
if G is not.
There was no G here, right?
Yeah, in the original theorem, H cannot be is always abelian, yes.
Okay, sorry, that was what else.
And then I confused you. I'm sorry.
By the way, it is abelian because it has dense abelian support.
Yes. Yeah. Okay. So but now you're basically done because you have now a transitive action of the compact group, and you just have to mod out one stabilizer group to get an isomorphism between your space and your homogeneous space. So now you take you choose just any point, any place point in your space K, and then you take U, the subgroup you look for, to be the stabilizer group of your group H or your uniform enveloping group, and then you get an isomorphism from HU to K, which just evaluates an element. That's it. Okay, and this and this gives you your rotation. And so in the end, you get in a canonical way your representation. So really there's not much to prove here. And then finally, the third step is to go back, and there you don't have to do much either, because I erase this. So of course, in the end, we want to have a representation of our measure preserving system with discrete spectrum. And we have found a topological model, and we've represented the topological model as a topological system, as a rotation on a homogeneous space. But now the third step, so transition back to ergodic theory. Now we see that xt is isomorphic to a rotational system, but with some, so first we just have here some measure mu, which comes from our model. However, since in our representation theorem, we actually obtain a map which has dense range. So I should probably add this in the topological formulation, but it's too far away, I will, I will leave it. So because C generates my group H, so C has dense range, I know that every invariant measure under the action is invariant under every element in the range, and then also in the closure of the range, and then also it has to be the Haar measure because it's invariant under every rotation. Okay, so this finishes the proof, and yeah, I should say that this topological part is also quite old, so you can find this basically in the same way in the book of Ausland on topological dynamics, for example. But let me now show you that basically you can use the same approach to also derive a version of this theorem in the relative setting for extensions of measure preserving systems. So this is the second part of my talk. So now we turn to structured extensions of first ergodic systems. Yes.
So when you define this extension of in this operator theoretic language, it is L2y goes to L2x, or it's not the other way around, or it's a molecular difference.
Sorry, I got lost.
It's in the top board.
Yes.
So that map is that's the orthogonal projection, or the conditional expectation. Is that map that the delta is giving you from L2y through to L2x?
I'm still lost.
The natural map from L2x to L2y,
yes,
given by composing with the.
Yeah, exactly. So if you have a concrete realization, then it goes the other way around, because your projection goes from x to y, and then j is just the induced operators of the pullback of this projection. I'm not sure, maybe I did not understand your question correctly, so maybe you repeat it.
Maybe if he will define extensions, maybe, because it's close to...
He defined extensions as already.
But maybe he will want to define the
I actually wasn't planning to do
extension, then I also would like to know what is an extension.
Okay, then maybe. So what I mean by an extension is really, I have a map from L2 of y to L2 of x, which is linear and is a Markov embedding. So it respects so it is isometry, it respects the absolute value, and it maps the one function to the one function. So this is.
But is there some structure similar to ergodic theory when the factor, if you have a factor that the whole.
You mean the conditional expectation?
Yes.
Yeah. Of course. So you can just take the adjoint of J. This gives you the.
Can I think of Y being a product space when X is one of the components?
Y being a product space.
You see, we take skew product on the torus, it has torus action as a factor, but the whole skew product is on two torus. So
here, why?
Yeah. So Y is the smaller system. You have to.
Other way around. So is
So so maybe if you have a classical, so say you have your skew torus.
I see.
Then J is just again given by composing.
So in that picture, the y is at the bottom.
The Y is the bottom, yes. So
this is evil.
yeah, sorry. But this
is contrarian, right?
Yeah, it's contrarian.
Okay.
But then still, is it then fair to think of X as a product space?
X, so this here.
Yeah, because in your example it is.
Yeah, but in general it is not so. I mean, you can have.
Orally, it should be close to a product space, no?
Well, if you take any.
Give us the decomposition.
No, product up to something, because you're very general, but exactly like with the skew product. It is a product space, but the action is.
Well, I mean, if you have.
Maybe it's.
It could be any factor, right?
I think
Yeah, if you have any, so
Yeah,
maybe forget
I'm
about.
looking for factors. That... Okay, keep going. Yeah.
Yeah, I mean, I'm pretty sure. So in what I do now, everything will be product, but this is not, in general, I think it's not the case that every, so every extension between measure preserving systems is given by a product of the.
In ergodic case, I think this is Rochlin theorem.
Ah, okay. I know what you what you were up to. Okay. Yeah, but I'm not sure. So I will just go on. Ignore your
He
question.
confessed of his sins about.
Okay, so now turn to the case of extensions. When we have just repeated what an extension is, so I actually wanted to do this. So that's good. So we now start from an extension. And now let me say what it means to be structured for this extension. And for this, we once again observe that this is actually an embedding of L2 space into the other L2 space. And so in particular, I can multiply elements of L2 of X with elements of L infinity of Y just by plugging them into J and then transferring them and then multiplying. So this, in this way, this becomes in canonical way module over this algebra of L infinity of Y. So this is why there is a suitable generalization of this concept of discrete spectrum, which was already used by Furstenberg. And I will write down what it means now. Yeah, it doesn't work. Maybe trying 3 times is not. So J. Sorry.
pull this one all the way up and only then.
Yeah, but then I cannot write here anymore.
Oh, yeah.
So okay, J has a relative discrete spectrum. Spectrum, or is isometric or compact, if you will. Means now that again I take my space L2 of X, and this is generated by a certain subsets. And in the definition before, we took finite dimensional invariant subspaces, and now we just replace subspaces by submodules, and we get the same definition, but in this relative version. So we take every M in L2, which is a finite dimensional or finitely generated invariant submodules. M is P invariant and finitely generated L infinity Y submodule. So this is the notion of structuredness we are looking for. And then there's also the same, there's also a representation, a geometric representation in this case. If we have ergodic systems, so if xt and then consequently also the factor ys is ergodic, then the extension has a discrete spectrum precisely if it is isomorphic to a skew-product extension. So, yeah, maybe I erase this now. So J has now a discrete spectrum if and only if J is given by a skew product. So say I will do this with topological data here. So I have a topological system, L psi. So again, psi is an action by continuous maps of G on the space L, a topological system, and some measure mu L on that space. So this corresponds to my ys. Now, now again the arrow is in a different direction because now I'm again on the point level. So there the map, the extension is just given by a projection onto the first component, and the system xt is given essentially as a space by a product. So again, I have this homogeneous space, and I take the product with my system or my space L, and the same I do with the measure. So the measure is also just, I take my measure on L and the H measure on the homogeneous space. And the only thing where I have to be careful is with the dynamics. And here these are given by now a co-cycle. So I now have a co-cycle from G times L to H. The co-cycle defining the dynamics. So at T, I act on an element here given by a point in L and an element of my homogeneous space by, in the first component, just applying my dynamics from here. So this is psi. And in the second component, I rotate with my co-cycle. So the rotation now depends on the point where I'm at. So I have this CTL XU. And we've already seen an example here. So such a skew torus where the projection, so here we just have the rotational system from before, and now here on the, so this is for a Z action, and the dynamics is just given by the first component. We take the standard rotation, and in the second component we have this skew rotation where the co-cycle in this case just given by the identity map on the torus. Okay, so so every ergodic extension which has discrete spectrum is of this form of the skew product up to an isomorphism. Okay, any questions so far?
So I would like to, I remember Mariusz and Weiss and Touvenot have some relative version of.
And this is related.
This is, so what is the connection?
It's the same.
But you're aware of the paper? There's paper.
Yeah, so this is also not, so I should mention who this is due to. So, so this is, so you can find this in the separable case in an article of Zimmer from 1976, and then Furstenberg also from 77. Both with separability restrictions, and actually, so this in this famous theorem, this famous paper of Furstenberg, where he proves Szemerédi's theorem, and this is also, so he uses this representation of isometric extensions to prove Szemerédi's theorem, to give his first ergodic theoretic proof of Szemerédi's theorem in this article. But there are also newer versions. So there's a version due to Ellis from 84, and then also from Asgar, Jamneshan, and Bergische in the uncountable case from last year, where this is presented in a slightly different form, but you can still get this result. Okay, so the result again is not new, but I will come to the new result in the end. I will just explain how to adapt the proof we just had for the Neumann theorem to this relative situation. So I will show that you can use the same topological approach. So,
and what you call relative situation?
Well, to have a system, so you have an extension and you have a property of xt relative to the system ys. So it is structured relative to the factor, so to say. So the system itself is not structured, but the extension or the system is structured relative to the factor. Okay, so yeah, so let's return to the same proof on the same steps we had just had. So the implication from B to A, this is again just the Peter-Weyl theorem. You have to think a bit more, but it's still the same argument. But the interesting direction is again from A to B. So what did we do in the first case? Well, we, as a first step, so we have our extension with a discrete spectrum, and in the first step we passed to topological dynamics. We defined a topological model, and we will do this here also. So change to topological dynamics again, and yeah. So now we have to choose two models, one for our system xt and one for our system ys. And the model for our system ys is just the maximal model or the canonical model or the stone model. There are different names for that. So you just take the corresponding algebra, which is L infinity, the whole space L infinity of y. So your maximal topological model that you can have. And for your second algebra, you do it as before. You just replace invariant subspaces by invariant submodules. So you take all these invariant submodules in L infinity and take the closure in L infinity. And then in that way, you get, again, a C-star subalgebra, which is dense in L2. So you get a topological model from this. So in the end, what you get is the following. So you may assume that your extension is induced by a topological extension, so a factor map now, a true factor map between compact spaces intertwining the dynamics. So we have an action on some space K, we have some action on some space L, and we have a continuous map between those, which is surjective and commutes with the actions. Okay, so we achieve this, and the extension now has the following properties. So before we translated the measure theoretic discrete spectrum into topological, and here it's the same. So this extension now has relative discrete spectrum in a topological sense. It is again the system K phi is topologically ergodic, so the constant functions are the only invariant continuous functions in K on K. And we have two additional properties which are important. So the first one is, let me start with the fourth one. The fourth one is that L is actually in our model here a Estonian space, or an extremely disconnected space. This is due to the model we chose. So here we have the Gelfand space or representation space corresponding to this L infinity, and you can show that this is extremely disconnected. So this is a Estonian space, a so-called Estonian space. And your map as a consequence of this model is also open. So it's not only continuous, but also an open map. Okay, so and we will now use these 4 points to show that we can again represent such a topological extension as a skew product in a topological sense, and then translate back to an ergodic theory in the final step. Okay, so okay, so the second step is now to show if I have an extension of topological system satisfying these 4 properties, then it is actually given by a skew product. So given by by projection onto the first component. And yeah, and now we have to remember what we did before. So in the first proof, we used this enveloping semigroup to construct our compact group, and here I will do the same thing basically, but we have to respect the relative structure of the problem. So now let me draw a picture. So this is our space K, this is our space L, and this is our map Q. And now I have these fibers of my map. And I will denote them by K sub L. So this is the pre-image of the point L. And before I look at the maps phi t from K to K, and I took the semigroup generated by the closure. I took the closure. And now I just cut them into pieces. So instead of looking at the whole map, I will cut it in pieces by restricting each map to every fiber. So I will restrict this to a fiber, and then it goes from the fiber to another fiber, which is just a fiber over the corresponding point moved here in L. So I will look at this set, and what structure does this set have? Well, it is contained in the space of all continuous fiber maps, we call them. So this is just the disjoint union of all spaces CKL, CKL tilde. So I just get this, the space of continuous fiber maps. I just take these all maps between fibers which are continuous. Now, before I took the closure with respect to the compact open topology or the topology of uniform convergence, now you can still topologize this space in a suitable way that generalizes this topology, this compact open topology. So you can define a compact open topology of this on this space as well, and then then you have one more obstacle, namely before you start with a group and you got a semi-group or a group by taking the closure. However, here it is not really a group anymore. It doesn't really make sense to compose a map going from this fiber to this fiber with a map from this fiber to this fiber. It doesn't make any sense. So this is no longer a group, but it is, or a semi-group, but it's still a so-called semi-groupoid, where this is a set where the multiplication is only partially defined. So you can only compose certain pairs of maps. And now by the same, so now you can still define the smallest closed sub-semigroupoid of this semigroupoid. And this is the so-called uniform enveloping semigroupoid. So there is still a canonical way to obtain an enveloping object in this relative situation of an extension, which gives you a lot of information about your extension, because using again these two properties, we get the same as before. But now for this groupoid or semi-groupoid, so now you can use one, and actually also this openness you need here to see that in our situation, if we start with an extension having these properties, then this is not just a semi-groupoid, but actually a compact groupoid. So it's compact with respect to the topology I mentioned, but it's also groupoid in the sense that every fiber map I get out in this, every fiber map which is contained in this enveloping object, these are all homeomorphisms. These are all invertible maps with their inverses again in the enveloping semi-groupoid. So in this case, this object is really a compact groupoid. And by using again this irreducibility condition, one can check that the canonical action of the groupoid on K, just again given by just putting in a point into a map. But now I have to be a bit more careful, so I can only, so I take here a fiber product because I can only put points into maps which are defined on the right fiber. So I can only, so my elements in my enveloping object are now maps from fibers to fibers, so I cannot take a point here and evaluate my map which is defined here. So I can only evaluate in points which are on this fiber. But again, part 2 of my 4 assertions here, or conditions here, implies that this canonical action is transitive. So I can really reach every point from every other point by using an element of my enveloping semi-groupoid or groupoid. So if I start with any point here, I can apply such a map to get to any other point in my space. Okay, and in particular, if I now pick again, as before, one fixed point of my space K, then and I take all, I take the so-called isotropy group over this point Q of X naught. So I take all down first. So I now take all maps which just map one fiber to itself. So for example, I take this point here, and now I take every map in my enveloping groupoid which maps this fiber to itself. So I forget about all the other maps in my groupoid for the moment, which are defined on other fibers. I just look at the maps which are defined on this fiber and map the fiber to itself. So, and I get in this way now really a compact group. So before I had a compact groupoid, and in this way I now have a group operating on this one fiber. So this is my H. And again, my U is just the stabilizer of that group. And so I again obtain in the canonical way an isomorphism from the homogeneous space, but now only to the fiber over my point, over my base point corresponding to X naught. So I no longer have an isomorphism between the whole space K and my homogeneous space, but only between this one particular fiber. So in the end, I want to get an isomorphism between these two spaces, of course. This is what I aim for. I want that my system is given by a skew-product and not this single fiber. And here I again use the transitivity, which tells me that I can reach every fiber from every other fiber by applying elements of my groupoid. And then you have to still do some work, but you can show that there exists such an isomorphism, but you have to use some results to Gleason, which allows you to do this in a continuous, so to transport things in a continuous way. So there's a selection theorem due to Gleason which allows this. So, and the third part, I will skip this, but this is basically the same as before with some slight modification, as every other step. So, but you have to trust me that you can also now, when you translate back to ergodic theory, somehow show that the measure is the right one. So it's just a product measure with a Haar measure. Okay, so now in the final few minutes, let me just tell you the real new result. So this is now the generalization to the case of relatively ergodic extensions. And basically, you can now use the same methods. Everything becomes a bit more complicated, of course, but in the end, it's the same method. Still, you still can use this enveloping semi-groupoid or groupoid to derive a representation in the following version. So there's again a separable version due to Austin from 2010. And now our version is from this year. Just it just appeared on the archive 2 weeks ago. So we have an extension from ys to xt. And now this is only relatively ergodic. And this means that so the systems do not have to be ergodic, but the invariant functions do not change. So if I take all invariant functions and put them into my J, then I already obtain all invariant functions on TO. So the invariant factor or the fixed factor of my system here is the same as here.
But one of them you do assume to be ergodic?
Sorry? If you assume one of, so if this is ergodic, then also this is ergodic.
Assume any ergodicity.
Sorry?
You do not assume any ergodicity.
No, I just assume that, so to say, the trivial part of the dynamic is not, doesn't grow.
It's the same as saying that the invariant functions measure with respect to y.
Sorry?
It's the same as saying that the invariant functions measure with respect to y.
Yes, yeah. Every invariant function is measurable with respect to the factor.
So the absolute case should be special case of what you're doing now, right? Because it's relative case.
Yeah.
In the absolute case, you did assume ergodicity.
That would be where y is the 1 point space.
Yeah, then y is the 1 point space, and then this just means that this system is ergodic.
If I'm interested in non-ergodic any structure, then this will not help.
If you have no ergodicity, then this will not help. But I will say something in the end, which I'm already down to almost. So what is the characterization now? So J has, again, relative discrete spectrum. So it's structured spectrum if and only if now my extension is again given by a skew product, but now a relative skew product. A relative skew product with respect to the invariant factor or fixed factor of my systems. So now I have my system L psi mu L as before, but now the skew product is actually a fiber product over the invariant factor. The measure is again some product measure with the H measure, but I will explain that. And the dynamic is again given by a co-cycle. So the difference now is that you do not have just one compact group and one closed subgroup, but you have a family, a bundle of compact groups indexed over the invariant factor. So you now have actually a bundle of compact groups indexed over the invariant factor of my system, and the subgroup bundle also indexed over. So this subgroup bundle of this thing. So this is the difference now. So you find. So let me draw a picture. So maybe your system looks like this. So you have two parts which are invariant. Then your fixed factor is 2 points. 1 and 2. And then now you have a group for each point. So you have a group here, which might be a circle, for example, and you have a group here, which might just be a trivial group. And then your skew product, your relative skew product would be, for one part would be a cylinder. So this times this. And here I just take this times this, so I just get this line. So this is the difference now. Yes.
So if everything were separable, what you would do is to use ergodic decomposition and just apply the.
Yeah, I think I'm not sure how Austin proves his results, but yeah, I think he uses ergodic decomposition stuff. Yeah, and some selection theorems, measurable selection theorems.
And so there's an implicit guarantee that this sort of they're changing continuously as you move around the base.
Yeah. This is what. So these bundles are topological. So these are continuous maps and even open. So yeah, So you can describe it again with topological data. You have continuous co-cycles, continuous bundles, and so on. So this is also one feature or advantage of this representation. Here you work with measurable data.
But you don't have a sort of locally constant condition because it's too much.
No, I don't think you can expect that. Okay, so let me finish by saying why this is interesting. So yeah, so I think Austin has some applications to Host-Kra structure theory, but I will have to look into that more in detail together with my co-authors. But at least from a structure theoretic perspective, this is quite satisfying, because if you start from any measure preserving system xt, then the Furstenberg-Zimmer theorem tells you I can recover it by building a tower, and I can just start that tower with the invariant factor. So I start the tower with the invariant factor, the fixed factor of my system, which of course here I have just trivial dynamic, so this is not that, that complicated to understand. And now I rebuild my system as a tower. And I have in the end some final extension which is weakly mixing, and the extensions in between are all have discrete spectrum, and these are all relatively ergodic because this factor is the invariant factor. There's in the other factors I do not gain any trivial part, and in this sense I can every of these extensions can be represented in that way. So I can really now represent the intermediate steps of this tower by geometric data. Okay, so thank you very much for your attention and the questions. So yeah.
Questions?
Yes.
So I guess in all these proofs, how important is this topologization step? So I sort of couldn't really figure out where the topology is essential for the proof and where it's just a sort of convenient place to live. I mean, for example, this when you take the closure of your operators and back open, could you phrase that on the measurable side if you try really hard or something, or is it?
Well, so for me, it's more beautiful to first prove the topological representation and then translate, because there you can work with points and you have no issues with null sets and so on. And so in the separable case, this also is shown by Austin, you can do everything with measurable structure, but somehow countability is built into measure theory in some way. And so it is, yeah, if you want to do some things uncountable, then somehow these Stonian spaces and the analysis on Stonian spaces comes up naturally. And yeah, this is basically what I can say about that. So for me, it is nice to also have a topological representation at hand and then get the measure theoretic problem as a corollary, basically.
Okay, but am I wrong if I think it, because the topologization result you're using is sort of on some level abstract nonsense, right? I mean,
yeah, you could say
wave magic wand and then this done. So, but what I don't know is if there's one bit of it that like turns out to be secretly very, very difficult to replicate without talking in that language. Does that make sense? Or...
Well, so yeah, I don't think you can really translate this topology directly to the measure preserving setting or to the measure theoretic setting. So maybe I can explain you what the topology looks like. Maybe this helps. So what does it mean that? So the problem is you have to say what it means for maps defined in different fibers to converge to some other map on a different fiber. So what you do is, so basically the convergence is given by the following. So if I have a net of maps converging to some other map, then these are defined on some fibers. And of course the base points of the fiber should converge. But also, so this is what I want is whenever I have a net of points here in these fibers converging to a limit point in in the fiber corresponding to the limit of my net, then I want that this converges. And so all these methods are very topological. So I don't know how you would write down something like this in a measure theoretic framework.
I see.
Okay, thank you.